Okay, good evening, guys. Hope you can hear me.
Good evening, sir.
Good evening.
Good evening,
How
sir.
are you guys? Good?
Yes,
Exams are
sir.
over?
Yes, sir.
Yes,
Okay,
sir.
great. Great, great. Hope you did well, right? Not only last time study and giving the exam. Okay, great. So hope you have the energy. It's evening, so I guess you have the energy to continue. Okay. I'm very happy. Actually, we have 19. So it's a good attendance, I'll say. And we are really good to go. Okay. So shall we start? Any one of you missed last class about internal pressure, design of cylindrical shell due to internal pressure? Any one of you who missed it? I hope I have shared that link. Okay, Sonar is saying, Amit, Sonar is saying he has missed. So Amit, have you seen that recordings? Okay, no response. So any other, because it will be difficult for you to understand if you have not got it. No, you guys have. If you have not attended, then definitely you should have seen this before coming to this class. And there was some homework given. Anybody remembers what was it?
Yes, sir, to find pressure of spherical pressure vessel.
Yeah. So the first was there are two homeworks.
For spherical
Yeah.
shells,
To calculate the thickness for a spherical shell, and the second,
This said, sir.
ellipsoid.
Ellipsoidal.
yeah, for elliptical head. Anybody attempted that for spherical shell?
Yes,
Okay, another
thickness is coming 16 and 1/6.
1/6, almost half of what we calculated for cylindrical, right?
Yes,
Why is that? Why spherical shell is having only half, or for the same pressure we need only half of the thickness? Why is that? Anybody can respond to that? Okay, Hitesh is saying even distribution of pressure. So cylindrical shell is not having even distribution. I can understand there are two different types of stresses which are there in cylindrical shell. It's mainly who are governing. Actually, there are three, but two are the governing thicknesses, governing stresses. What are those two different types of stresses which we generally calculate?
Circumferential stress.
and longitudinal, right? Though two types are there, circumferential and longitudinal.
Sir, in spherical, it is longitudinal stress are not there. I think so.
So
So
both are
only
same.
Okay, so if we say that, Hitesh, that if longitudinal stresses are not there, if circumferential stresses are there, then the thickness would have been same, right? Because the same formula will be applicable. So actually there are only one type of stresses in spherical because it's a spherical shape. So there is no longitudinal and circumferential. Actually, there is one type of stress which you can say it as a longitudinal. Actually, the name does not make sense for that because there is no length, right? So, and neither a circumference kind of thing because it's a spherical. So, whatever is coming along the a shell which is like it's going inside the thickness. So, if we just want to, I'll just share my screen so that we can just show you something. Okay, this is the calculation last time we had. So if we want to draw that, consider that as a sphere. So it will be along this line. Okay, so in this line also, and if we see in the other view, it will be all same. Okay, so only one type of stresses, but the stress generated in spherical are only half of that magnitude, half of the magnitude of the circumferential stress which is generated in a cylinder. Okay, and that is the reason if we design the vessel in a spherical shell form, we will get the thickness only half of whatever we have to give for a cylindrical. Making sense, guys? Is it making sense?
Yes, sir.
Yeah, great. So now you tell me, you might be thinking now, then why not to always go for a spherical shell rather than going for cylindrical? What do you think? Which type of vessel are generally used? A cylindrical type of vessel or spherical? If you might have seen any in any plant, if you might have visited, what type of
Cylindrical.
The cylindrical.
cylindrical?
Cylindrical.
So why is that when you are designing, you are finding this as a more economical because the thickness is almost half. Then why we don't go for spherical?
So construction is simpler in case of
Yes,
cylindrical.
correct. And who is that? Who responded?
Arshad.
Harsha. It's very good. So exactly the right point because the construction of spherical shell is really challenging. Okay, it's really difficult. And then support, you have to provide a leg kind of support. That is also only point support you can give. So it becomes critical. So that is the reason it's less in use. But still, if you have a very high pressurized fluid, okay, like LPG storage, it has to be stored at very high pressure. So for very high pressure components, still it makes sense to provide a spherical shell. So many times you will see that. So once you see a spherical shell, you should remember that definitely the pressure is going to be higher in that. Okay, that is the reason they might have gone with spherical shell. And whatever the cost you save in material, that is a huge cost. Okay, and then it will be sometime it may be more than your construction cost. So finally that economics works out to be in favor of spherical shell. Okay, so that is about, I hope if you have not calculated the thickness, please do that. It will hardly take 5 minutes. I'll just open the section. Last time we calculated for circumferential stress for a cylindrical shell. So this we did. and this was given to you as a homework. So very simple formula. If you calculate, do you want to do it now? You guys want to do it now if you have not done? You want to calculate the thickness, or we should go to the next section? Whatever you say.
No, sir. Please calculate it back.
You want to calculate it? Okay, let us calculate. It's better to spend 5 minutes and so that, see, once you calculate it, it will start making more sense to you. So you have to do it one time at least. So try to do it. So let us do that. Let us try to calculate. So what we'll do, we'll just copy paste the formula here. I'll just take a snapshot of it. We'll paste it here. Okay. So now what we are going to do is to calculate thickness for spherical shell.
सर
Yes,
सर प्रेशर जो है 20 बार वो डिजाइन प्रेशर है कि इंटरनल प्रेशर?
internal design pressure. It's a design pressure. All the margins are already taken. Clear, Ahmed? Or you wanted to ask something else?
राइट सर, जो सेकंड सेशन में डिस्कस किए थे,
Yes. So this was the
वन
design pressure 20 bar.
एटमॉस्फेयर आउटसाइड रहेगा, इनसाइड रहेगा, तो एब्सोल्यूट और डिजाइन प्रेशर माइनस कर देते हैं. दैट
Yes.
इनसाइड में 20 है, आउटसाइड 1 है, तो 20 माइनस 1 तो
Yes, you are
19 होगा.
very right. But here we have considered this as a design pressure, not see, normally as a mechanical. See, that was for concept. Okay. So normally that is already done by the process, and when we get the input, we get, see, not only the difference, but they have to take some margin also, right? Because if in the operation they feel if 20 bar pressure is going to be there, they will give you 1.2 times, 1.3 times higher pressure. Okay. Because in process sometime it may have, it also needs some tolerance, so they want to keep it higher. We don't want to exceed the design pressure. So your question is very valid. So if nothing has been said to you and it's given as a pressure like 20 bar, so first of all you need to ask whether it's 20 bar in absolute or in gauge terms. Okay, so you should ask that. If it is in gauge terms, that means already that external pressure has been subtracted. Making sense?
यस सर.
if
Yes,
if I
sir.
give this input in absolute terms, then you will be designing your pressure vessel for 19 bar. 20 minus 1, which is there for the external, which is trying to oppose it, okay, which is always going to be there. So 20 minus 1, we have to design only for 19. Okay, but if it is given as gauge, then this is the resultant. Okay, so that is the reason we
यस सर.
always take gauge, because gauge will always give you the resultant. Okay, so
यस
20 bar will take, and we will design for that. So now let us do that again for spherical. So what was our pressure? It's 2 MPa. 20 bar gauge means 2 MPa, right? What is the radius? We'll take the same radius which we took for cylindrical shell, equal to this. This is the diameter, so radius will be half of that, right? We'll take a spherical shell with radius of 1250. There is gain corrosion allowance of 3 mm. Okay. All other things like allowable, we can just take same, because we want to keep the temperature same. So this allowable at 400 we have 101 MPa. Okay, this is in mm. Okay, efficiency we
So
want to
radius 1253.
sorry
Radius are 1253, right?
1253. Right now we are just taking the inside radius. When we calculate in formula, we'll take that, right? Sorry, good point, right? So thickness now we are calculating. So we know that we always calculate the thickness for end of life, right? So when for end of life we are calculating the thickness, pressure is going to be same 2 into radius, like I think Mobasi said, right? So we need to find the corroded radius. So corroded radius is going to be more, because once it corrodes, your radius is going to increase, right? Any confusion in that, guys? Anyone who might have not attended
No,
video?
sir.
We have spent a lot of time last class, right? So someone who is new might have that confusion, but if you go to that video, I think then it will start making sense to you. So what we did, 2 SE, okay, minus 0.2 times again P. This is the thickness which you are getting. Okay, so only 12 mm. When we calculated for cylinder, if you remember, this was the thickness. Okay, so this was the thickness for circumferential stress, and this was for longitudinal. So now you see it's matching with longitudinal stress thickness because of longitudinal stress. So that is the reason we say that the stresses in spherical shell are longitudinal in nature. Okay, but actually the name itself does not make sense because there is no longitudinal in spherical shell. Okay, but does not matter, there is only one stress and it has half of the circumferential stress which is there in the cylinder. So thickness also half. Making sense now? So this is the corroded thickness. I cannot take that and design. I'll have to add the corrosion allowance. So my minimum design thickness, I'll say that TD will be this plus corrosion allowance, right? I need to take this. So if this is the minimum thickness required for design, which plate thickness you will select? What will be
18, sir.
18? Okay, why not 16? Now we are talking about the nominal thickness. So T nominal. So now the question is whether I should take 16 mm or I should take higher. So what is your opinion?
So whichever the standard thickness is near.
Okay, so 16 mm. See, normally the even values you will get in market. So 16 mm will be available. So shall I go with that?
So
Yes, sir.
That is very true when we have a cylinder. Okay, in cylindrical shape, normally the thinning is less. Okay, now you know that it's a spherical shell. You will be forming petals. In petals also, normally we do forming, and it is the thickness reduction is less, but you can take some margin if the you know See, this is where your interaction with the fabricator who is going to fabricate that becomes very important. Linking between the design and the fabrication process. So you should be aware that how much thinning may happen. Generally, that is not known to the designers who are not experienced. So that time what we do, we mention in the drawing itself that 16 mm or let us say 15.4 mm we will write in the drawing as minimum thickness. We'll write to both of the thicknesses, okay, 15.5 as a minimum, and if we have selected 16 mm, then this we will write as a nominal thickness. So now if the same drawing is given to the fabricator, he knows that this is the minimum thickness which he has to meet after forming. Okay, there is no margin here. If it goes below, your design is not qualified. So you cannot go below this thickness. Okay. So now if he thinks with whatever process is going to follow, with that process, if the thickness, if he uses a 16 mm plate, he will not be able to meet 15.4. In that case, he will decide to take 18 mm. Making sense?
Yes, sir.
Yes,
Yeah,
sir.
sir.
So if you have any doubt, like if you think that the process normally for cylinder it does not happen, for cylindrical shape you only rolling is required to achieve that shape, so your thinning does not happen. Okay, so that time if we just give a nominal thickness, that is sufficient. But if you make a formed heads like 2:1 torus spherical, okay, or a spherical shell, in that case even for like spherical shell the thinning will be less, because if you know the construction of a spherical shell, it is in petals form. Okay, it's petals construction. If you don't know what is petals, you just try to see that in Google, or in YouTube you will see that construction of petals. You will find lots of shapes. It will make more sense. Like it will be a segmented things. Do you want to see it now, or you are aware you want yourself to see? What is it? You want to see it? What are the petals? How they look?
Yes,
Yes,
sir. You
sir.
can show it.
Okay, let us search in Google. See, petals are the name is from not the petal of flower. See that? See this construction? So lots of different segments. You can see that welding here, right? Here they have tack welded. They'll finally weld it. So it's kind of petal, like we see in flower. See that? The center portion is crown. So crown and petal. So in center it's a spherical piece, and outside you'll see. So these are the dishes. So normally this construction, even if we want to make a hemispherical dishes, in that case also that petal formation is required. Okay, because only by forming achieving that hemispherical shell is very difficult. Making sense now, guys?
Yes, sir.
Yes, sir.
Yes, sir.
So whenever you feel some terminology which is you find it difficult, just note it down. You can always see it. Okay, once you see it, then it will make more sense to you, right? Then you will understand it better. See, mechanical, the advantage is that you can see everything. Okay, So once you see it, it becomes pretty clear to you, what we are trying to do. Okay, we are not trying to invent anything. We are just trying to do a simple job. Okay, great. So we have the thickness now, so we can go with 16 mm. Okay, for spherical shell, because we know that the petal construction will be there, so thinning will be less, and we'll like to give him the minimum thickness also, so that he's aware. He'll be aware that because of his forming, this is the thickness which he has to meet anyway. Great. So now, shall we go to the next topic?
Yes, sir.
Yes, sir.
Great. Okay, so before we go to uh, thickness calculation for different types of dish ends, like elliptical head, due to internal pressure, shall we go for the external pressure thickness calculation for a cylinder? What you want to do? You want to finish the internal pressure part and then go to external, or you want to finish the cylinder part first? What do you want to do?
So I guess cylinder part
Channels.
is
Yeah,
completed and it will be better.
external separately will cover.
Yes, sir.
Okay, so first we'll finish the internal pressure part, right?
Yes, sir.
Okay, great. So let us go to section UZ32, okay, where we have a formed heads. Okay, so now we'll just brief what we did again, so that you are in line. What we are trying to do is to make a vessel. Okay, so when I say a vessel, at least these three parts will be required, right? Like if I can show you, I can just open PV light, and there you will see that different parts. So that will start making more sense to you. Instead of drawing, you can just directly see. So for a vessel, a typical vessel, I'm trying to say, so the main pressure parts are the cylinders and the dishes, right? So if we have these three parts, first of all, we need to qualify these three parts for internal pressure. Okay, that is the main pressure for which my process requires that pressure to be contained by this vessel. Okay, that is the reason why we are making this vessel first of all. So it has to contain that pressure. Okay, so let software, it will open, and then we'll see that these three different parts. Okay, and
सर ये फॉर्मूले में लेंथ कैसे इनपुट कर सकते हैं
formula में,
लेंथ
हाँ, we'll see.
जनरेटर लेंथ
Now that's what I was coming to. So now what we did till now is we have calculated the thickness for a cylindrical shell for design pressure. But have you used the length of this cylinder for internal pressure calculation?
नो
No, right? So
No,
what
sir.
does that mean? Whether it means that length does not matter at all for internal pressure for a cylindrical shell? Can I conclude like that? See,
Yes, sir.
yeah, yes, please go ahead. See, when we saw this internal pressure for shell, okay, the L is not at all defined here. Okay, in none of the formula it's coming. So if I make a statement saying that length does not matter at all for internal pressure calculation, so I am 100% correct. Okay, it does not matter whether I'm designing a 10-meter long or 20-meter long or 30-meter long vessel. As long as it is internal pressure, only that radius is important, not the length. Making sense?
Yes.
So the three parts which we are trying to say, this is here I have selected elliptical. So this is an elliptical head. Then there is a cylindrical shell. Again, I will add a elliptical. So this is my vessel. Okay. There will be nozzles, supports. Okay, those will be there, but these are the three main elements. So what we have done till now, calculate the thickness of this cylindrical shell. Now we want to calculate the thickness of this elliptical head. That is what we want to do. Clear? So for that, we'll go to section UG 32. Okay. So UG 32, I'll go to, see, before that the definitions are there. We'll come back to the definition. So after seeing that formula, if required, we'll come back to that. This is the formula for elliptical head. Okay, before we go to the formula, we'd like to discuss whether, once I say elliptical head, what do you think? Which kind of shape it is? How many radius it will have? A typical ellipse will have how many radius? Did we discuss that last time?
Yes.
We discussed, Ahmed,
Yes.
about elliptical, multiple radiuses, major, minor. We discussed that.
No, sir. No, sir.
Okay. So, like if I try to draw an ellipse, okay, this is the ellipse, right? How many radius it will have?
2.
Two.
sir.
Okay, I have two different answers. One is 2 and one is no, sir. So, no, sir means what? How many?
Major or minor, sir?
Okay, major and minor, so 2, right?
Yes.
Yes, sir.
Yes? All are agreeing to that?
Yes, sir.
Yes, sir.
Yes, only. Yes, sir.
Yeah, Dakshat?
Yes, sir. Only 2 radius, major and minor radius.
Okay. Okay. So this is my major diameter. This is my minor diameter. So actually that minor diameter will have the highest radius. Major diameter will have the lowest radius. What about in between? If I ask you, so the two radius you have given, okay? Now, if I ask you what is the radius at this point, whether it will be equal to the radius which is at minor dia or at major dia or in between something.
In between.
In between, right? So that means at each and every point there will be different radius because that is how it is made, right? So your answer, like two radius are there, but two radius are only for defining that ellipse, right? So that it's not that elliptical head will have only two radius, it has infinite radius. Okay, the two different radiuses are there. Between these two values it will vary, isn't it? Making sense?
Yes, sir.
sir.
Yes, great.
Yes, sir.
Yeah, clear to everyone, right? So it is elliptical head. There will be two radius, but that two are required as an input so that we can draw it. But once we draw it, we know that at each and every point the radius is varying. Okay, but when we try to fabricate this kind of addition, it becomes really difficult to even form and also to inspect, because there are multiple radius. So how many time I'll take the value and measure it, or I need a template which is exactly machined so that I can keep at least a D by 4 sector template which I can keep and see that there is no gap. Okay, so the forming wise and inspection wise it becomes difficult. Now let us talk about a torus spherical shape. Do you know what is torus spherical? Elliptical is a very common shape we have used, but have you any time used torus spherical word? Any one of you? Okay. Now let us see that what is a torus spherical. See, unlike elliptical head, your torus spherical is having only two radius. These two radiuses are called, one is crown, okay, which start from here till here. It's crown. And there is a small radius which is knuckle. So torus spherical will have two different radius. One is crown and one is knuckle. Making sense?
Yes, sir.
Yeah. So it looks like elliptical, okay, but it is defined by two radius, while elliptical will require infinite radius. Okay. So torus spherical, the fabrication and inspection becomes easier. Okay, that is the reason it is famous in fabrication. When we do actual fabrication, we prefer addition which is a torus spherical type, so that I have a two radius by which I can define it. It will be easier for me to fabricate and also to inspect. Okay. So, but then why elliptical at all we are going? Okay, we'll come back to that. So now if you see code, there is a elliptical head. Okay, there is some formula given, but then there is a statement given here. I want you guys to just read it. Okay, if any one of you might have tried the homework, they would have seen it. So I like you guys to read it and we can discuss about it then. So first of all, I hope you understand what is 2 is to 1. You guys know what is 2 is to 1?
Yes, sir. No, sir.
No? So 2 is to 1 is nothing that it is the ratio of major to minor. Okay, major diameter divided by minor diameter, or major radius divided by minor radius. The ratio, if it is 2, then we call it as 2 is to 1. Making sense? Because your elliptical may have lots of different ratios, right? If a ratio is like this, then it may be 4 is to 1. If it is 1 is to 1, then what it will become?
Circle.
Circle, right? It is a cylinder. If the ratio of major to minor is 1 is to 1, then it is a cylinder. Now I start stretching it, so here I can say it's roughly in 2 is to 1 proportion. I can further stretch it. Now maybe it's 4 is to 1, right? So it can have various proportion, isn't it? Now again you can try to read it and just try to make out what code is trying to say, so that you will, inculcate a habit of reading a code. So I hope you guys are reading it. That's the reason I'm silent. Finished? Any one of you has finished?
Yes, sir.
Okay, Keshav has finished. Great, Keshav. So like to explain?
Sir, actually, the code is asking us to take the knuckle radius and the spherical radius as per the given dimension for any general 2:1 ellipsoidal head vessel.
Okay.
So
So
if
yeah.
we have diameter of 100, then 17 would be our knuckle radius, and
Mhm.
90 would be our spherical radius for
Okay.
the crown, for the
Okay.
dish, for the head.
Hums. You're right. For crown. So there are two, crown and knuckle, right? So crown is also written as spherical. So spherical and crown are same actually. So you can either say
Yes.
crown radius or you can say spherical radius. Okay. So you're very right, but one point you're missing. See, if I'm talking about 2:1 elliptical head, why I need crown and knuckle? When I say crown and knuckle, then I'm talking about torus spherical. So why code is mixing elliptical and a torus spherical head? Okay, it's linked to the reason which we discussed just now is that the
Because the
yes, Harshad,
means that
please.
the ellipse is having the infinite radius.
Yeah, correct. So because the elliptical, see, we prefer 2:1 elliptical head. Okay, and you will come to know why the reason once you calculate the thickness of the elliptical head. See, the elliptical head thickness will generally comes equal to the shell thickness. Okay, so if there are similar thicknesses in my vessel, definitely that will be a preferred choice, right? So we prefer elliptical head, but it's difficult to fabricate. So why not make it easier? So what they have decided that when we say 2:1 elliptical head, that will be actually a torus spherical head having knuckle radius 17% of the diameter and crown radius 90% of the diameter. So generally if you draw this shape, it becomes very closely matches with the elliptical head. Okay, that is the reason this ratio they have decided based on the reason that it matches closely with the elliptical. So now we are avoiding the problems in manufacturing because of infinite radius, and we are getting an elliptical head because we love that. We love elliptical head because the thickness is normally matches with the shell, or it will be very close to shell, so there won't be a too much difference in thickness. So once we have dissimilar thickness, the stresses are more at the junction. We don't want that. So if we don't want that, we prefer elliptical. Okay, making sense now, guys?
Yes, sir.
Yeah, great. So now we will come back again here. Now you know when we talk about elliptical, what is the shape we are talking about actually. So D is defined. Now we don't know what D is, whether inside, whether it is spherical, what it is. So we'll just see the definition of it. Okay. So anywhere, if you before going to the formula and going into the calculation, you try to see the definition of it. So D, if you see here, is the inside diameter. So that is, it is talking about a head skirt. Okay, so we are not concerned about head skirt here. We are concerned about elliptical head. So we'll read this statement. Inside length of the major axis of an elliptical head. So once we are using that d in the formula, d is what? It's the inside length of the major axis, means this one. Okay, when I say d, we are talking about this. So definitely this d, finally it has to match with the shell, isn't it? So my shell, the descent ID and the shell ID, that should match, right? If we see the sectional view of it, just to make it clear for you guys. Okay, we want this ID to match, isn't it? So if this ID is matching, that means my major axis for this elliptical head will be equal to the, guys,
ID
Diameter of the
yes, diameter of the ID, whatever we took, for the new condition. The same D will be there for this also. So right now we are just taking D as a, without corrosion lens we are taking as a nominal diameter. When we insert in the formula, that time we'll change it. So this is the D. P is already there. Other things are all common. Okay. So now if I calculate the thickness, let us modify it here itself so that it will be easier for us to write in the formula. So what D I should take now? If I want,
2506.
yes, if I want a corroded thickness, I'll have to include the corrosion lines, or I'll have to, the right way of saying is to, I have to exclude the corrosion lines, not include, because I want a corroded vessel. I want to design for end of life, not only the start. Okay. Now let us make it. So T is equal to, I'll just take pressure from here, P into diameter divided by 2 times S, as we have taken here also. So again, from here I can take S, then E is anyway 1, but we'll take that as an input, minus 2.2 times P. Right, making sense? So what finally the minimum thickness we got? 24.8. This is the minimum thickness required. But I need to provide a corrosion lance, right? So with that minimum design thickness, when I say, for that I need to add the corrosion lance. So this is my thickness. Now what should be my nominal? What should be my nominal thickness?
30.
30. See, 28 mm thickness also I can get in market.
Yes, sir.
What you want to select? Which thickness?
30.
Okay, 30, then why not 28?
Sir, it is very near to 28. The value is very near.
So you want to take some margin, but margin is for what?
Sir, for forming processes, if anything is done.
Yeah. So now we are talking about descent. Okay, so addition, the forming is very important, and when we do forming, if you see the knuckle is having very sharp radius. So once you have to make a sharp radius, there that thinning happens. Fiber elongation is more. In code, fiber elongation formula is also there. Okay, so the thinning is more in knuckle because it has a sharp radius. So once I have to form a addition, I need to take margin for the reduction of thickness. So once I take 28, I don't have any margin. So normally, how much thinning is expected? The maximum thinning is expected as 10%. Okay, that is the maximum thinning which is expected by the process. So if I say the 10% of, let us say I've started with 30, what will be 10% of 30?
0.3.
3, right? 10%, isn't it? So if 3 mm is the thickness reduction which may be possible, so if this is the thickness reduction at the knuckle, then my thickness after forming may be 27, okay, which is lower than my minimum design thickness. So I want to be in safe side, right? So I'll go with this 32, because even if 10% reduction is there, that is the maximum. Please note down. So if the fabricator is very confident, if he can maintain his thinning within, he can always go with 30 mm. That is the reason for addition I need to give minimum design thickness and nominal both. So he'll be concerned about the minimum thickness. That value will be available to him, okay, so that he can take his decision whether he want to go with 30 or he want to go with 32 or even higher. Making sense? So here I will go with 32 mm thickness. Making sense?
Yes, sir.
Yes, sir.
Great. So this is how your thickness will be calculated for a elliptical head. So for cylindrical, we got 30 mm. Okay. For elliptical, 32 mm. It's very close. Okay. So there is no lot of difference in thickness. What about tori spherical?
Sir, that 10% thinning is applicable in this case only or in every case?
In this case means for elliptical head you are asking?
Yes, sir.
Yeah, for any forming like elliptical, tori spherical, where you have a sharp radius. See, crown is very big. So once you have a bigger radius, the thinning is not that much. Once you have to form a very sharp, your fiber elongation is very high. So it will be applicable for all type of decisions. Okay, or any other sharp bending if you are doing for that shape also. But that is the maximum which is expected. Okay, it's a kind of thumb rule. Not it's not a backed by code that is only it will happen. It will depend finally which process the descent is formed. Based on that, the thinning will be there depending upon process to process. So it may be less, it may be more, but generally it does not go beyond 10%. So that is a kind of thumb rule.
Okay, sir.
Great. So now we'll go with tori spherical. Tori spherical shell, you already know how tori spherical is same. It will have two different radiuses. Okay, but now here, like knuckle was 17% of the diameter, here your knuckle is only 6% of the crown. Okay, now what is the crown radius then? Crown radius equals to the OD of your OD of the skirt. When I say, it means OD of this. Okay, this is the straight length of the descent is called the skirt. Okay, making sense? So your knuckle is 6% of the crown, and your crown is equal to the OD of this descent. Making sense? Yes, no, confusing?
So can you repeat?
Yes. So as you know, for a torus spherical we need two radius, right? One is crown and one is knuckle. If I have these two radiuses, I can draw a torus spherical. So torus spherical can be of lots of different shapes, right? It can have lots of different ratios, different diameter. So ASME has defined, like if I want to use this formula, this is applicable for a torus spherical having knuckle radius. Knuckle means this radius, okay, the knuckle portion, or we can say this also, this knuckle. So knuckle radius as 6% of the crown. So it will be clearer once we calculate it. We are going to calculate it, so I think that will be better. So we just calculate, it will make more sense to you. Okay, so shall we calculate?
Yes, sir. Yes, sir.
Yes, sir.
Just a minute, I'm having a call. Yeah, sorry, there was a call. Yeah, so let us calculate. Okay, then it will be pretty clear to you. Okay, so first of all, we'll start from here. First decide what is crown, and then we'll go to knuckle. So the crown radius equals the outside diameter of the skirt. So crown radius, if you see how that crown is, which word they are using for crown radius, if you go here, so L is the inside spherical or crown radius. Okay, so if I take this L, so how they are defining, it's the equals to the outside diameter of the skirt. How I can calculate the outside diameter? Do I have the inside diameter?
Yes, sir.
Yeah, it's what it is? 2500, right? So if I add twice of thickness, then I'll get the outside diameter, right?
Yes, sir.
Clear to? It's very simple, right? I have ID, okay? I want OD. So OD is nothing but twice the thickness, isn't it?
Yes, sir.
Clear to everyone?
Yes, sir.
Okay, but now the problem is the thickness is what we are trying to calculate, isn't it? Then how I can add the thickness and get the OD? Making sense?
Yes, sir.
No? See, if I have to find OD, I need thickness, but the thickness is what we are trying to calculate. Okay, so if you want, you can use, if you're good with equations, you can use a T here. Okay. Or you can take any thickness, assume like 32 mm, do calculate L, okay, and then again do the iterations. If the thickness which you got is 40 mm, then again you have to calculate and see whether that how much L is changing. Okay, and then what is the final thickness? You keep on doing unless you whatever you assumed and whatever final you got, unless it is matching, you have to do the iteration. So which part you want to do? You want to do the assumption? We
So
can
whichever
try.
way it is,
Sorry.
so whichever it is convenient.
Okay, so what I can do, let us first take assumption part so that it will be much easier for you to understand. So what I'm trying to do, I'll just assume a thickness, okay? So I can assume whatever we got for 32, means for elliptical. Let us see whether, so once you do the process, then it will be clear. So just see what I'm trying to do. So I assumed before, because I wanted OD, right? So what I did, I assumed the thickness so that I can get the OD. But you have to remember that this OD, I have made the assumption and then calculated. So if my assumption is not correct, I'll have to again assume it. Okay. So 2 times the thickness, I got L value. Making sense to everyone?
Yes, sir.
Okay. But now this is the crown radius. So it is inside. So finally, this will be my L when my crown is new. When it is corroded, it is going to increase, right? So I'll have to further add the corrosion allowance here. Okay. Now I have the L value in corroded condition. I'll just copy paste the formula so that we can see and then calculate here. Okay. So L value I have. Now if I have to calculate the T, then 0.885 times pressure. You guys can also do the calculations, okay, so that if I make a mistake, you will be able to catch. S is the allowable stress into E, okay, minus 0.1 times gain pressure. Oh, what thickness we got now?
45.
45.
So,
We started with 32, so definitely if I take 45 here, definitely my L will be changing, and if L is changing, your thickness will change. Okay, so this thickness is not final. Now I know that roughly 45 mm I'm going to get, so I'll start with 40. Again I'll change my assumption, change to 45. So once I take 45, I can see that it's very close. Let us take 45.5, very close, right? So if you want, you can take 5.4. If you want to match with two digits also, 5.6, 5.5, I can take in 5.5 it will match. Okay, so now if I can take this assumption, so if you do in Excel sheet, it will be much easier for you to do the next calculation. Now I can see here it's matching. If I make this to only two digits after decimal, it's exactly matching, right? So now I'm good. Okay, so this is my minimum design thickness. I'll just again these things I'll have to do. This is my minimum required thickness. I need a minimum design thickness and a nominal thickness. So here I'll have to add corrosion lines. Okay, and then here I'll have to see if I take a 50 mm. If I take a 50 mm, then I know the 5 mm thinning, with that I'll get 45. Okay, but I need 48. Okay, so I'll have to start with 55. 55 I'm getting what is required, so I can even take 54. Okay, this is good. So I'll have to take 54 mm as nominal. Clear, guys? Any doubt?
No, sir.
Yes, sir.
Yes.
सर ये assumption कैसे की?
Assumption मैंने just ऐसे ही कर लिया है. I can take even 10 mm assumption. Anything I can take. Assumption के लिए कुछ दिमाग नहीं लगाना है.
फिर ये सर आप बोले कि मैच होना चाहिए.
वो बाद में मैं मैच कर रहा हूँ ना, शुरू के लिए मैच नहीं करना है.
मतलब दोनों मैच सेम आना चाहिए.
हाँ तो वो बाद में कर रहा हूँ ना यार मैं.
Sir, we can simply stick to equation part.
Yeah, we can
We
do that
got
also.
45.605.
Yes. So who was having that doubt about assumption?
Me, sir.
Okay, Ahmed. So Ahmed, there is no problem in assumption, right? Like let us say you assume to a 10 mm.
Yes.
Okay, with 10 mm, what thickness you got is 44.
Yes.
This till this you can do, right?
Yes, sir.
So now you got 44. Now you know, right, that I have assumed very less. So if I increase the thickness, my L is going to be more. So thickness also will be more. So I'll have to change my assumption. Now I know, right? In the first step, I was not aware. So now I know that my thickness assumption is not correct. So now I'll take 44 mm. Still my minimum. Now I can see the calculation, right? I'm knowing the output. So now I can definitely make the assumption, and finally I can make it closer to what I need.
Okay, sir.
Clear, Ahmed? Anybody else is having this doubt, or clear to everyone? Guys, okay?
Yes, sir. अभी दूसरा मेथड भी है ना.
So other methods you guys can try. See, now you guys are engineers. You should be able to tell me the next method. If you don't do the assumption, what you will do? T is here. L is the L you can write in terms of thickness, right?
Yes, sir.
Right or wrong? It's not anything so sophisticated or complicated, yeah. L, by using the same formula here, I can write it in here only. I have to add T. I'll have to write just T. Now, okay, now you guys can try. Okay, now it has become a equation. T here and here also T. So try to solve it and tell me the value. Understood, right? Hitesh, Ahmed, Akash, Aman.
Yes, sir.
So please do that and tell me what thickness you're getting. So Ninad has calculated as 45.6, very close to what we got.
The same 45.55.
Correct, right? So finally, either you use that or you use this method. See, this I can assumption I can do because I'm using Excel sheet, so I can, you know, multiple calculation or iteration is not a problem, right? If you do by calculator, then each and every time you have to put the values. And clear to everyone now?
Yes,
All
sir.
both the two methods, right? Ahmed, Ahmed, is it clear?
Yes.
Okay. So just solve that equation and you'll get the final thickness. You can use any of this method. Now you see the thickness comparison. For cylindrical, you got 30. For elliptical, we got 32. For torus spherical, we are getting 54. See the difference in thickness. Finally, this 54 you have to join with cylinder, right? So there will be a dissimilar thickness. So stresses will be more because of dissimilar thickness. That is not a problem, but you know, that is one factor for selecting elliptical. Elliptical is more popular because of this reason, that the thicknesses will be same. Clear, guys?
Yes, sir.
Okay, now one homework I'll give it to you. You have to calculate the thickness for hemispherical head. You can do that.
Yes, sir.
It's very simple. Only that L is there. Now I want you to see how you are going to use it. So if you want, you just calculate it and post it. Don't wait for the next class. Do the calculation, take a snap, and post it in the group. Okay, keep it active, guys. So whatever you have, if you are reading in between, if you are reading any clause, if you have any doubt, please ask in the group. So other also who might have not got that query will be benefited from that, because everybody will benefit. So we have to learn from each other. Okay, great. So internal pressure, you guys are pretty clear. You can do the calculation for different types of dishes, for cylinders. Now we'll come to external pressure, right? Shall we move to external pressure now? Guys,
Yes, sir.
Nickel head is also there.
so we are now going to see thickness calculation. We are coming back to the shell. Okay, now we want to check the shell thickness which we selected for internal pressure, which is 30 mm. Okay, now I'll have to check that whether the, we know external pressure failure is different, right? The buckling occurs. Okay, for external pressure, the shell may buckle and collapse. There is no failure by yielding of that material. The failure is because of collapse. Okay, and collapse, if you know by the name itself, you might be feeling that it's always instantaneous. It's very, you won't be able to visualize any deformation. It will not give you any indication that it's going to fail. Suddenly it will collapse, right? So it's very dangerous. The external pressure failure is very dangerous because it's very instantaneous in nature. It will not give you any indication. So now let us check whether the thickness which we have selected for internal pressure, whether the thicknesses are, just a minute, yes, I'll take a call and come back. Yes, so now we'll calculate the thickness for external pressure. So let us start with our first item, which is shell. So we have already the thickness 30 mm. So now shell, will have, I'll have to qualify this 30 mm or some other thickness. Which thickness I'll have to qualify? Guys, you guys are there?
Yes, sir.
So shall I qualify and start with the 30 mm thickness, or I'll have to qualify the end of life thickness, which is 30 minus corrosion? Which one? Which thickness I need to qualify?
End of life thickness.
End of life. Any doubt in that? You guys are thinking too much. So we are doing all the calculation for end of life, right? So we need to qualify this 27. So if 27 is able to take that external pressure, then we are good to go. Now, what is my external pressure here? We are trying to design for atmospheric. Okay, so definitely if the full vacuum is happening inside the vessel, then your full atmospheric pressure will start acting. Okay, and that, it's, let us see, we have 1 bar, so we can call it as 0.1 MPa pressure, which is there because of atmosphere, and it will start, it is always there. Okay, but you don't have to design your cylinder for external pressure always. You have to design only when there is a chances of vacuum getting created. I hope it makes sense. We have covered that in detail in first class itself. So I hope there is no confusion in this. So P external is now 0.1 MPa. Now let us start the procedure. Okay. So we are at UG 28, thickness of shells and tubes under external pressure. So there are some definitions. The procedure starts from here. This is where your procedure starts. So first of all, the step 1 is to check whether my D by T ratio is greater than 10 or less than 10. Because if it's greater or equal to 10, then I can follow this procedure. If it is not, then there is a different procedure, okay, which is covered in 2. So let us check that first. So what I need to do, I need to see that DO divided by T. DO is the outside diameter, right? If you want to see, you can see the definition. DO is the outside diameter of the cylindrical shell course. Okay. So now I need to find out what is my outside. So before calculating D naught by T, let us first calculate DO. What is DO? Tell me. Tell me
DI plus
fast.
2T.
Yeah? Again, please.
DI plus 2T.
Yes. Very true. So you can tell me the value also. Is this correct? 2560?
थिकनेस कौन सा बोलिए सर एंड ऑफ लाइफ 32 या जो इक्वेशंस है 32
Okay. Again, that end of life and this thing has come. Who has asked that, by the way? Who asked that question? Ahmed.
यस सर
Good. So now let us discuss that. You guys tell me which one to take. Anyone can answer that? If I am calculating the OD, which thickness I should take?
27.
27. So Mubasir is saying 27. Anyone else? So finally then it will become 2560. I'll just write this in here. So it will be 2500 plus 2 times 27. That is what you want to say, Mubasir, right? Guys, what about others? Which one is correct? Or you have a different value? Just think clearly, there's a very, you yourself can decide which one to take.
So
If
we need to take for the end of the life then
yeah,
2554.
that is true. See, that is definitely we have to take for end of life. But then what is the value? How you will calculate that? Which calculation is correct then? Because this is not the value which will have end of life.
Sir,
मैन्युफैक्चरिंग तो 32 mm के शीट से की है
Yeah, one by one. Ahmed, what you want to say?
सर ऊपर जो थिकनेस आपने सिलेक्ट किया वो 32 है और जब मैन्युफैक्चरिंग करेंगे तो 32 mm का शीट ले करेंगे कैलकुलेशन में वो आना चाहिए
No, I could not understand what you are saying.
सर थिकनेस 32 लेंगे ना
We are talking about shell. For shell, we calculated 30, right? Design thickness. That we did last day, in last class.
30 लेंगे क्योंकि मैन्युफैक्चरिंग 30 mm की शीट ले करने तो जो
See,
प्रोडक्ट
tolerance
बना है
thickness.
अपना वो
Now we are not discussing about the manufacturing tolerance. On that we have already discussed, and we have decided 30 mm. We are going to take. Now we just want to calculate the OD of it.
30 लेंगे
So means 2560.
यस
See now, anyone else like to respond? Which one of these is correct or any other value?
Sir, 2560.
2560. Hitesh is also saying 2560. So now if I ask Hitesh, why you are
Yes.
not taking end of life?
Sir, because it is outside diameter, inside diameter, it is not inside diameter. So inside diameter has its corrosion allowance. Sir,
Correct.
outside we
Outside
don't.
we are not expecting. So now, Mubasir, see, once you want to calculate the corroded condition, right? So in that case, the ID which you are taking, that will be G2506, right? With that, if you do 2 times thickness, again you are getting the same thickness, right? Because OD is not what is changing, only the ID is changing. OD, there is no corrosion lance, it's painted, we can maintain it, so we are not expecting corrosion there. In this case, I'm not saying it won't be there all the cases. In the case which we have selected, there is no external corrosion lance. Making sense, Mubasir? Confused? Please tell me. Mubasir, Ahmed, any confusion? Or
No, sir.
anyone else? Aman, Akash?
No, sir.
No,
Clear,
sir.
right?
But yes.
Yeah. So see, even if you are calculating end of life, what I did, I took, see, once you are taking 27 mm, which is the end of life thickness, you have to select the ID also for the end of life, right? So if ID is selecting for end of life, that is 2506 plus 2 times the thickness which is there at the end of life, you'll get the same value. Okay, because OD is not changing. Okay, so now we have the OD. Now we can calculate DO by T. DO is there. Now the thickness which you are taking, it will be 27 or 30.
सर एएसएमई देखना पड़ेगा
हाँ,
एएसएमई का कोड देखना पड़ेगा ना सर
कि कौन सा लेना है?
यस
इसमें तो बोल दिया ना, जो भी फॉर्मूला में अगर टी बोला है, so टी इज ऑलवेज कोरोडेड ना. ये सभी में तो क्लियरली बोल दिया, जो भी फॉर्मूला whatever is given, the formula is all in corroded condition. So
Sir,
टी क्या होगा?
256.
2560 divided by 27 or 30?
37. 27.
27
27. Hitesh, you are saying 30?
So this is confusing a lot.
But what is the, that's what the reason we are discussing it, right? So that it should not become confusing. So if you can tell me why you are taking 30, then we can discuss why it should 27. Why you think it should be 30?
So because 30 is the nominal thickness that we got, and
Yeah,
27 we will take for 27.
27. Right? So you are also convinced. So by yourself you have convinced, right? So others also convinced, because see, the DO we are not taking as, see, 2560 is still at the end of life. DO is maintained because there is no corrosion allowance. So at the end of life, this is same. The thickness is going to corrode. So we'll be taking 27, because we all the time we are designing for end of life. That philosophy is not going to change. Okay, so if you put a little bit logic yourself, you'll be able to convince that what value you have to take.
Sir, that ratio will not having the unit.
Yes, that's very true, because it's mm divided by mm, so we don't, it is not a, it will not have any units. Very true. Okay, so now we have the d by t ratio. It's called a ratio actually. Okay, after this we'll see what code is trying to say. So d naught by t, if value is greater than 10. So in our case we are getting 94, much more than 10. So definitely we can follow this procedure, isn't it? So we are ready to go to step 2. So now we are at step 2. In step 2, what we will do? Okay, in step 1 we have to calculate one more ratio, which is L divided by D naught. So now you see that L is coming into the picture. This L is nothing but length of the cylinder. Okay, right now we are only focused on this shell, so that L which we are taking is the shell length. Okay, once we are calculating for the full vessel, it will be different way. Come back to that. But now my cylinder length is 10 meters, so L is 10 meter divided by DO. This is one more ratio. Okay, once I have, this is your step 1. Okay, so we started with, see, for external pressure you have to assume thickness. We are assuming a thickness, right? But in our case we have already calculated the internal pressure, so we are sure that, you know, even if 20 mm is qualified for this pressure, can I take 20 mm, guys?
Yes, sir.
If 20 mm is qualified, can I take 20 mm for shell thickness?
No, sir. It's
No,
high
right? Because
because
for
No.
internal pressure I know that 30 mm anyway is required. Okay, so if I take here 20 mm and it's qualified, then I'll have to again do the iteration. I have to see if I want to calculate what exactly is the thickness, okay, where it is going to collapse. That time we'll have to keep on reducing the thickness and finally finding that value, which is the thickness where it will not be able to take. So if I want to minimize my iterations, I can just take the thickness same as what is required for my internal pressure. So assume the thickness 30, and based on that we did this calculation. Now we are at step 2. In step 2, code is saying that enter in section 2 part D sub part 3. So ASME section 2 part D, we know it's for material. Okay, so allowable we have already referred for internal pressure, but allowable was in which part? Allowable stresses are given in which part? Do you remember?
Subpart.
Subpart 1, right? If you just, I have opened that section 2 part D. So if you just see this, subpart 1 is the stress table which we referred when we did the calculation for internal pressure for allowable stress value. So there is subpart 2 for physical properties like modulus of elasticity, density, thermal expansion coefficient. For those values I can refer subpart 2. Subpart 3 is applicable for external pressure. So this ratio which we get by L by D and we denote by T, for that there is a figure G. It is called a geometrical chart. Why geometrical chart? Because it all depends only upon geometry. There is no other factor. No pressure, okay, no temperature, nothing. Only based on geometry, because it depends only on L by D and D naught by T. Both all are part of geometry. Okay. So now we can definitely enter here. So it's saying that subpart 3 figure G, which we have already opened, and enter at L by D value. What is my L by D value? It's 3.9. So at 3.9 I have to enter the chart. We'll draw a line so that it will be easier. So 3.9, we can say that there is no 3.9, it will be very close to this. I can safely take it very close to 4 mm. 4, not mm, 4 ratio. Okay, this is the line where I have to enter. What is the other line? That is d naught by t, L by d naught and then d naught by t. Now I'll enter with the d naught. What is my d naught by t value? It's 94.8. So d naught by t value, if you see 50, 60, 80, 100, 125. So it will be very close to this 100 value. So now I cannot draw a straight line because it's a line which is not linear. Okay. So now this is the line, right? You have to very closely follow that. Okay, this is the line. Okay. Now it's 94, so I can take it maybe a little bit here. It will all be approx. Okay, now this is the intersection value which we got. So this intersection value, I'll just draw a vertical line now, and this vertical line I'll move to the intersection. Okay, so this is what we will be getting. Now anybody can read this value what we got?
1, 3.
Yeah, tell me that value. See, please remember it's a geometrical graph. It's not a normal graph. Tell me the value.
3.3.
3.3, 3.4.
So directly 3.3.
That's
See the downline. Start with 0.41, then 0.31. So these two which you see, what is this value? It's not 2, it's 0.0002. This is 0.0003. So this value will be 0.0032 we can take. Clear? Yeah? No confusion, right?
Yes, sir.
Okay. So now I can take this value. We have got factor A. That factor A value we have got. That is this value. And this is from figure G. You guys can know, I don't know what you have to prepare for like this internship if you have taken. This kind of program you can make in this Excel sheet. What we are doing right now. And this can be your project for what you did in this internship. Okay, so A value you got. Now what is next? We'll go to code. So this is all about calculating that factor A. Once we have that factor A, okay, in this step 3, once we have that factor A, we have to again go to subpart 3, and then we have to go to the material under consideration, that material chart. What is this material chart? So if you remember, when we are referring this stress table 1A, which is applicable for section 8 division 1, if you go to 516, okay, we are too much ahead. We have to be in carbon steel. Sad. See, if you remember, when we are referring this carbon steel property in table 1A, Okay, so if you go to page second, the same line 38, you see the chart CS2, which is your chart for external pressure calculation. So once you have calculated that A factor from figure G, you have to go to a material chart applicable for your material that you can find from the stress table. So for this it is CS2. For 516 grade 70 it's CS2. So now in section 2D, okay, once we are in this sub part 3, okay, after this figure G, if you move down, there is first figure which is CS1. We don't have to refer CS1 because we have to refer CS2. For us, this is the applicable chart. Making sense, guys? Till now?
Yes, sir.
Yes, sir.
Clear to everyone? Yeah. So now once I am in material chart CS2, I have to enter with the factor A which we have already calculated. What factor A value we got? 0.0003 and 2. Roughly we were here, right? So it will be difficult to draw a straight line like this. I'll just draw it here and then I'll bring it to now it's straight. So I'll just move it like this. Now I have the factor A line. What will be my other line? You can see that there are multiple lines given based on the temperature. 150, 260, 370, 425. What is our temperature?
400, sir.
400.
400, sir.
400, right? So 400 is the design temperature. So if I go again in this table, so we have line for 370 and 425. Where my 400 line will lie? I can assume it
Above 425.
almost, no, almost in the center. Okay. So here the gap is wider, where we have to find the gap is almost, negligible, does not matter. So if I just make a line like this, it will represent 400. Then I'll draw a vertical line and then I'll move it to exactly to the intersection. Okay, now this is the line which is cutting this factor B at what value we will read this. This is 25, 30, 27.5 will be in the center. We can call it with a 28. Can I call it 28 MPa? So factor B
Yes,
is,
sir.
so we can write, we have found that factor B value, and then this factor B which we got from this chart is 28 MPa. Once I have this factor B, this is my step 3. In step 4, I'll again come back to the code, section 8 division 1, my design code. Now we'll go to this. Once I have this factor B, I can use this equation to find out PA. What is PA? PA is the allowable pressure. How much pressure your 30 mm or 27 mm thick cylindrical shell will be able to take, how much external pressure. Okay, so if I use this formula, then we'll calculate PA value. So we have 4 times B divided by 3 times D naught by T. D naught by T ratio we have already calculated. So we'll take from here. So this is 0.39 MPa. If we convert that into bar, it will become 3.9 bar. Okay, what was the pressure, external pressure for which we were designing? It was only 1 bar. Okay, so now PA value is greater than my design, external design pressure. So my design for external pressure is safe. Can I say that?
Yes, sir.
Yes, sir.
Making sense, right? Yeah.
Yes, sir.
Okay, so this is what is the procedure for calculating that external. This what we discussed is for internal pressure. Now there is lots of, or not lots of, small if and buts. If you have some different value, like if I go to this chart, now your query should be like, if what if this line is coming like this? Okay, I can get this ratio also, right? Factor A ratio, if it is like 0.40 and then 4, then this line will be like this. It's not intersecting any line. Or it can be like this also on the right hand side. So if it is completely on the left hand side, you will see that there are lots of steps which we left. Okay, so if you see the value A, if falls left to the applicable material temperature line, then PA can be calculated like this. So there is no B. Directly by using that A value and modulus of elasticity value for the material for that temperature, you will be able to calculate the PA. If it is in the right hand side completely, then in case where the value of A falls to the right, assume an intersection with the horizontal projection of the upper end of the material temperature line. That means if this is my temperature line, okay, and this is where it's ending, so with the end I'll draw a horizontal line, okay, and wherever it is intersecting with the vertical line which is there, this will become my value. Okay, making
ये
sense?
ग्राफ में E की वैल्यू क्या है?
E की value,
Yeah, looks like.
this is the E value, no, modulus of elasticity. It's not efficiency. This is the modulus of elasticity value. Okay, so this, if you are getting this V value like we got in our case, we don't need that modulus of elasticity value. Okay? We don't need that in this formula. But if your A value falls to the left hand side, then you will need it. Okay? You will need that E value because you have to use this formula. Making sense? Yeah? Yeah?
Yes, sir.
Clear, guys? So hope this external pressure, now you know, as example, you can take different values and do some calculations, so that you become perfect for doing these calculations. So any if and buts you'll be able to take. Okay. So I hope today's class was, you found it interesting. Okay. And hope you enjoyed and learned a lot.
Yes, sir.
Yes, sir.
Yeah. Great, great. Good guys. So it was really good. We had a good discussion also about corrosion and thicknesses after corrosion. So I hope now it will not trouble you again. Just trying to think logically, it will not create any problem to you. Okay. Okay. So next time, try to calculate. One exercise I've already given to you. What was that? You have to calculate the thickness for internal pressure for a hemispherical. That is the first thing. Second thing is kind of sorry, a kind of optional. If you do it, that is good, and that will be try to calculate the thickness for the dish ends for external pressure. Okay, we have calculated for the cylindrical shell, internal and external. For formed heads, we have calculated the internal pressure thickness. The external pressure is still balanced, right? So if you can do that, that will be really great. Okay, making sense now, guys? Is it
Yes, sir.
is it difficult or it's easy to use code? Now it's looking pretty easier, right?
Yes, sir.
Yes,
Better than.
sir.
Yeah, great, great. Good, guys. Okay, let us meet in next class.
So
See
action
you
से
then. Bye bye.
sheet पे share कर.
Bye, guys. Bye bye.